The next section of chapter 4 deals with energy exchange. And these terms go back to one of the prior chapters, but we'll talk about conduction, which is the transfer of energy from warmer to cooler molecules. Think of this as when you put a pan on the stove and you turn the stove on, heat is conducted through that pan from the stove into the pan into then whatever you're cooking, right? And convection is heat energy that's carried by moving warm air or water. And this goes either direction. Wind chill factor is maybe an example of convection, where if you go outside and it's windy, you get colder. Heat is leaving your body. Air is blowing across your body that's colder than you are, and it's pulling heat out and moving that away. Latent heat transfer is that water absorbs heat as it changes from liquid to gas. Examples of this will include transpiration from plants, but also think about when you're hot, you sweat. That sweat evaporates and cools you down. And then radiation from the sun. Now, this equation can be a bit scary, so we're gonna walk through the diagram and then walk through the equation. So what this diagram is showing is a plant with some leaves. There's solar radiation coming in from the sun. A certain amount of that bounces off based on the color, shape, and the type of the leaf. There is heat loss through evapotranspiration. So water that's lost from the plant cools the plant. There's infrared energy coming in, and some of that is bouncing out or being released out. Some of that's through the photosystem, some of that's through chlorophyll. And then we have heat convection and conduction, and then heat conduction to the rest of the plant. Now, some of these terms are always positive, and some of them can be positive or negative depending on what's going on. So if we have delta H plant, what that's saying is change, delta is change of heat for the plant. So if we want to figure out how the plant's going to fare under a variety of conditions based on temperature, these are the factors we need to think about. So the first is solar radiation. Obviously, the degree of intensity, time of day of the sun is important, plus the amount of infrared radiation coming in. So these are, I guess solar radiation could be a zero, and same with infrared radiation, but they're never negatives. And then infrared going out is always going to be a negative. That's a loss. Now, heat via convection or heat via conduction. Again, convection is wind. Conduction is through molecule to molecule physical contact. Those can be positive or negative. It depends on the temperature of the plant and the temperature of the surrounding environment. If it's going into evening and the plant's warmer than the air, there's going to be heat loss via convection. If it's in the morning and the plant's cold and the day is warming, it could be a positive via convection. So these are both positive and negative. It depends on the context. And the last one is heat loss through evapotranspiration. That's always going to be a loss. Whenever water goes from liquid to gas phase, that requires energy, and it takes that energy from the plant via heat. So evapotranspiration is always a negative. They're losing water, and with that, they get some cooling effect. And when we talk about animals, sweating is an example of that. But evapotranspiration is one way that plants can cool themselves via loss of water. And so plants can adjust the energy inputs and outputs. Transpiration rates can be controlled by specialized guard cells surrounding the leaf openings called stomates. Stomates. There's a couple different ways of pronouncing it. I've heard stomata before, or stomates. One second. Sorry about that. We're back. And the variation in the degree of opening and number of stomates controls the rate of transpiration and thus leaf temperature. So some plants can actively open and close these depending on the time of day, and other issues like water stress, things like that. So here's the stomate here. It's this opening or pore. And it has these guard cells that can open and close this opening. This is an infrared image showing temperature. So the temperature scale is here on the y-axis. Cooler temperatures for cooler colors for cooler temperatures, and hotter colors for hotter temperatures. And here we can see a plant with the stomates open. It's generally cooler. It's more down in this range of 21 degrees Celsius. And here's the same plant with the stomates closed. You can see that the leaves are much higher. Now we're up in the mid 20s. So a pretty big temperature change just based on how the plants, I was going to say monitoring, but that's the wrong word, gradating or adjusting the stomates to deal with loss of water and also temperature regulation. So to do this, to reduce their temperature, they also need to release water. So those two things are tightly correlated, is the ability to take in new water and to regulate temperature via stomates. Another way that plants have adapted to reflecting solar energy and reduced loss due to conductive heat loss is pubescence. And pubescence in this case refers to small white hairs that grow on the leaves or the surface of a plant. So these small white hairs do a few things. One is they're white, so they reflect solar energy, but they also provide a form of insulation. So you can think of it almost like fur, where when the wind blows, instead of interacting directly with the leaf, it's being deflected off these pubescent hairs, and it's also helping kind of insulate the leaf as well. And so here, this is an example of a summer leaf and the amount of reflectance it has compared to a winter leaf with solar radiation and infrared radiation. And then what this graph shows is along the x-axis is wavelength. And so in these wavelengths, we're primarily looking at solar radiation. And in these wavelengths, we're looking at infrared radiation. On the graph here, on the y-axis is percent reflectance. So the higher number here, the more energy is being reflected. You can think of this as like a white car versus a black car. Which one is reflecting more radiation? And so here, for the summer leaf, across the spectrum of solar radiation and infrared radiation, there's a higher reflectance, meaning for a certain amount of energy going in, the summer leaf is able to reflect more of that energy back out, which conversely equals absorbing less of that energy. And then during the winter, the leaf has less pubescence and it absorbs more of that energy. It has a lower reflectance. So this is like a seasonal response to, during the summer, not wanting to absorb a lot of energy, trying to stay cool. In the winter, perhaps needing more of that energy, so reducing the amount of pubescence on each leaf. So you can follow this as the winter line on the bottom and the summer line on the top. And then if air temperature is lower than leaf temperature, heat is lost by convection, related to the speed of air moving across the leaf. Now, boundary layers are important here. It's the zone of turbulence due to friction next to the leaf surface. Boundary layer thickness is related to leaf size, surface roughness. Small, smooth leaves have a thin boundary layer and lose more heat than large, rough leaves. And we'll take a look at this. I think the next graph shows it. I'll walk through it in the next image here. So if we have a smooth leaf, you've got the air is moving across that leaf in a laminar sense, and it's pulling heat off as it goes. If you have a rough leaf, it creates more turbulence, and you can think of this as like eddies. And instead of wind passing a smooth leaf, picking up energy as it moves across, if wind moves across the rough leaf, these boundary layers are increased, they're larger. It's this like eddy of circulating air that instead of that air picking up heat and moving on, it's just cycled around and around and around and forms almost like a insulative cushion around the leaf. We can think of the same thing when we get in like oceanography around ocean bottoms and how that relates to laminar and turbulent flow are typically the two words that we use. But the same thing happens here with leaves. And so it's one way that plants can adopt their physiology depending on whether or not they need to retain heat or if they're trying to lose more heat via convection. In cold, windy environments, convective heat loss is a problem for plants, so most alpine plants hug the ground surface to avoid wind velocities. And some have a layer of insulating hair to lower convective heat loss. So you can think of this as small, low shrubs that when the wind is howling down the mountain, they're protected because they're typically in a complex environment. They're not living on a flat surface, that there's a bunch of boulders and things and like that then break up that wind flow and reduce the amount of wind energy hitting the plant, so they can adapt by being smaller and closer to the ground where the wind forces are less severe, as well as adding things like small insulating hairs that break up that wind flow, so the wind directly hitting the leaf is sort of refracted off and slowed down by those hairs, which creates more turbulent flow, which provides, you can imagine, an insulating pillow around the leaf. Here's a example of that. This is a snow lotus. It has a dense pubescence surrounding the emergent flower stems, which provides thermal insulation. So it's starting to flower and it has this like dense hair all the way around it, which is helping keep helping reduce energy loss via convection. So it's providing a kind of insulated bubble around it. Now, for animals, the equation is primarily similar, but when we think about animals that generate heat internally, we need to add another term to balance the equation. So here, instead of delta H plant, now we have delta H animal. Change in heat within the animal. Solar radiation, again, always positive. Infrared energy in, always positive. Infrared energy out, always negative. Change in heat by convection or conduction depends on the relationship between the environment and the organism. If the environment's warmer than the organism, then you have convection and conduction being positive, adding heat to the animal. If it's colder than the outside temperature, or vice versa. If it's cold out and the animal's warm, these terms will be negative. The animal will be losing heat via convection and conduction. We can also have loss of heat through evaporation. In this case, sweating is a primary mechanism, as well as panting, like dogs will pant, licking the body, anything like that to have evaporation happen, which will provide a net cooling impact on the animal. But here we have a positive term, which is heat from metabolic heat generation. So through burning energy, there's heat produced, and that is a positive. So one extra term here. And then the way that evaporation is dealt with is a bit different. But generally kind of the same. You can think of sweat glands and stomata as being kind of the same thing. Generating heat internally has an advantage. Animals that can generate heat internally can maintain constant internal temperatures near the optimum for metabolic functions under a wide range of external temperatures. And as a result, these animals can extend their geographic range. And so via producing heat internally and then having mechanisms to insulate and keep that heat in, animals can now expand their range beyond where they would not be able to if they could not generate internal heat. And so hopefully these terms are reviewed, but we have ectotherms and endotherms. Ectotherms regulate body temperature mainly through environmental exchange with the external environment. Ecto, outside, therm, temperature. Ectotherm, outside temperature. Endotherms, endo, inside, therm, temperature. These rely primarily on internal heat generation, mostly birds and mammals, and ectotherms generally have a greater tolerance for variation in body temperature than endotherms. You can imagine if you are a reptile in a southwest desert, it's going to get extraordinarily hot during the day, and it also gets extraordinarily cold at night in deserts because there's no thermal capacity. The sky's clear. Heat rises. There's no large water bodies to regulate and moderate those swings in temperature. So in those environments, you would have to deal with massive temperature changes. Generally, ectotherms are better at that than endotherms. And some organisms that generate heat internally include bees and some fish, such as tuna, and even some plants. Skunk cabbage warms its flowers using metabolic heat in the early spring. And so there's some exceptions to this idea of like mammals and birds being the primary endotherms. Here's an example of bees generating heat by contracting their flight muscles, and the heat generated is a defense against Asian giant hornets, the killer hornets that we now have showing up on our shores. So they can swarm it, make a bunch of heat, and then basically cook the giant Asian hornet, generating temperatures of about 47 C, which is 117 Fahrenheit. So it's kind of an interesting mechanism there. And then heat exchange in the environment depends on the surface area to volume ratio. Smaller surface area relative to volume decreases the animal's ability to exchange, meaning gain or lose heat. And as body size increases, surface area to volume ratio decreases. Large ectotherms are thus improbable. What this is saying is, one way to think about this is the surface area of a sphere. Surface area increases with the square, and volume increases with the cube. So if you have a basketball, and I don't know sports. If you have a basketball and a golf ball, pretend the golf ball is perfectly round. So a basketball and the golf ball. The golf ball will have a large surface area compared to its volume. So if you calculate the surface area of that, divide it by the volume, you're going to get a larger number than if you take a basketball, measure the surface area, and divide that by the volume. Because as the sphere gets larger, the surface area is increasing with the square, length times height, effectively, right? But the volume is increasing with the cube. And this is an important factor in like phytoplankton size and energy absorption. It's also a big rule in primarily mammalian ecology called the Bergmann's rule. And this graph is showing average body mass of a moose in kilograms on the X, and on the Y, latitude. So the higher the latitude, the larger the number, the nearest the pole, and the larger the size. And what this is showing is a positive relationship between latitude and size. The idea behind this theory is that when you live in cold environments, staying warm is a primary driver for selection. If you're a big animal, you'll have a relatively small surface area to your volume or weight. What that means is you'll have a lot of mass and a small amount of area for that mass to lose its heat. You have less surface area, less skin that's losing heat via convection and conduction. If you're a smaller animal, you'll have a relatively more surface area, skin, compared to your volume or weight. So at higher latitudes, there's a big selection, or colder habitats, a big selection for larger bodied animals because they're able to hold and retain that thermal mass, their body heat, more efficiently than a small animal. Now there's, with any of these, so-and-so person rules, there's always arguments, and there's some arguments around Bergmann's rule. And there's arguments about what I'm about to say, but I think it does hold. This is a map of the distribution of white-tailed deer. White-tailed deer is the largest game species of deer in this country. And white-tailed deer extend down through Mexico up into Canada. And a white-tailed deer in the Sonoran Desert is referred to as a Coues deer, and they're tiny. They're smaller than our even like island blacktail deer. So they're very small deer. And one of the ideas is that they're small because they need to lose a lot of heat. They need a lot of cooling. And so they have a larger surface area to volume ratio, where in northern areas you have your largest, all of your like largest weight white-tailed deer come out of northern areas, particularly like western Alberta. And the idea there is it gets very cold, and so animals are larger to help retain that heat. So a larger animal has less surface area per weight or per volume. There's been some arguments back and forth about other mechanisms that could generate a similar phenomenon, but in general, I think that the underlying principles behind the Bergmann's rule make sense, and it, to me, is following first principles. So it's one way of explaining what the chapter is talking about in relation to surface area and volume. And then for small aquatic ectotherms, they remain the same temperature as the water. Some large ectotherms can maintain a higher body temperature. So what that's saying is if you're a small fish, insect, if the water is 10 degrees C, you're going to be 10 degrees C. But some large fish, particularly tuna, have the ability to use muscular heat and the way that they circulate their blood. They can maintain body temperatures that are up to 14 degrees Celsius warmer than the surrounding seawater. And this is kind of a classic example of the way that blood moves through the muscle tissue of a tuna. And here we can see the outside of the tuna. This is a cross section, so imagine you cut this tuna and just cut them in half. There's the vertebrae, and here's the two main muscle groups, the two main red swimming muscles. On the outside of the tuna, it's 19 degrees Celsius, and on the inside, it can be up to 31 degrees C. So that's a big, big difference, and these are like the super athletes of the ocean, right? Tunas swim really far, really fast, and by being able to maintain heat internally, the muscles are more efficient. And so this has an advantage to them. Of course, it's also using more energy, and so they need to consume a lot of food. And many terrestrial ectotherms can move around to adjust temperature. Many insects and reptiles bask in the sun to warm up after a cold night. But this also increases the risk from predators. When you just wake up and you haven't had your coffee and you're laying on a rock for all the world to see, there's a good chance you're going to get picked off and eaten. So with that, many of these organisms have developed camouflage, and they can change coloration to match their background. Here's an example of marine iguanas moving to a sunny location to warm their body before going about their daily activities. So this is something we see quite frequently. You kind of think of reptiles as slow in the morning or sunning themselves. Ectotherms in hot environments can gain too much body heat from the environment and reach lethal levels. Climate change appears to be limiting the foraging periods for several species of Mexican lizards, whose abundances have decreased significantly. So they also, because of their lack of ability to regulate temperature within themselves, their feeding windows are dependent on when they can go outside and be warm enough to move around efficiently and not too warm where they overheat. And so ectotherms in temperate and polar regions must avoid or be freezing or tolerate freezing. Avoidance can happen, so seasonal migration to lower latitudes or microhabitats that are above freezing, i.e. burrowing. And tolerance minimizes damage associated with ice-forming cells. Some insects have higher levels of glycol, which lowers the freezing point of their body fluids. And then for endotherms, there's a cost to be an endotherm. One is the high demand for energy, i.e. food, for metabolic heat production. So endotherms need to consume more calories pound per pound because we're burning a lot of those calories to generate heat. And metabolic rates are a function of the external temperature and rate of heat loss. So if you go outside in the cold with very little clothing on, you're going to burn more energy than you do if you're bundled up in a parka. The rate of heat loss is relative to body size and surface to air volume ratio. Again, back to the kind of Bergman principle. Small endotherms have higher metabolic rates and need more energy than large endotherms. So if you're big and large in a cold area, you have an advantage of having relatively small surface area given your volume. And volume here is a proxy for weight. Mammals in the Arctic have a lower critical temperature than mammals in tropical areas, so and the rate of metabolic activity increases more rapidly below the lower critical temperature in tropical mammals compared to Arctic mammals. Got a few more here. Evolution of endothermy required insulation, fur, feathers, fat. So as organisms start generating heat internally, then mechanisms for maintaining that heat became important. Insulation limits conductive and convective heat loss. Fur and feathers provided a layer of still air adjacent to the skin. And some animals grow thicker fur in the winter and shed it in the summer. So fur, it helps trap heat in via an insulated bubble of air, and then as the wind blows, it's blowing across the hair, not blowing across the skin, where it would pick up a lot more heat via convection. Small mammals have a thin fur and not much fat for energy, but a high demand for metabolic energy below the lower critical temperature. They survive in cold temperatures by entering a dormant state called torpor. Body temperature and basal metabolic rates are low, which conserves energy. So torpor can be thought of like as a mini hibernation. Energy reserves are required to come out of torpor. Small endotherms may undergo daily torpor to survive cold nights. Longer periods of torpor is called hibernation and are possible for animals that can store enough fat energy. So it depends on the size and the fat stores of the animal of what they're able to do. Here's a graph of a marmot that's undergoing torpor. And so we have time here on the x-axis. And on the y-axis is milligrams of oxygen consumed per hour. And then body temperature here is here on the second y-axis. So red is the amount of oxygen consumed per hour. So if we start here as the animal is entering torpor, it's consuming a fair amount of oxygen, and it's dropping down to a very little oxygen use. And then when it awakes or arouses, that amount of oxygen shoots up and then can kind of come back down, but it requires a kind of activation energy. And then for body temperature, it's similar, where body temperature is dropping from starting off in about 34 degrees, coming down to about 11 or 12. So that's a big change. And then when it awakes again, body temperature then increases and then kind of comes back down and stabilizes. So that's for a torpor of about 8-9 days. And so they're able to conserve energy by going through, you can think of it like a series of mini hibernations for a couple days, come out, feed, go back, enter state of torpor for a week or so, and then do it over again. That way they don't have enough fat or storage to be able to go through a full hibernation, be able to hibernate all winter. But they're able to kind of come in and out as a way of really reducing the amount of energy they need, both by allowing their body to cool and then using dramatically less oxygen. Okay, we're going to end this one here, and when we come back, I think we are moving on to water.